All right, ready to dive deep. Particle physics time.
Always a good time for that.
We're looking at this research report from way back in 2011, all about jet substructure.
Oh yeah, back when the Tevatron and the LHC were both running. Those were the days.
Like a snapshot of what we knew back then.
Yeah,
So imagine like smashing protons together,
at insane speeds, of course.
obviously. And then these collisions, they create all these particles, right? And they often cluster together in these things called jets.
Like a shotgun blast of energy.
Exactly. And this report, it's all about analyzing what's inside those jets.
Trying to figure out what made that blast in the first place.
Exactly.
Yeah.
But one of the big things they had to deal with back then was, what was it called? Pileup.
Ah, yes, pileup. The bane of every particle physicist's existence.
Right. Like, how do you even start to make sense of it all when you've got so much going on?
Because you've got these protons colliding at such high energies, you often get multiple collisions happening almost at the same time.
So it's like trying to have a conversation at a rock concert.
Exactly. It's a mess.
So how do they even begin to untangle that mess?
Well, they had some clever tricks up their sleeves. This report talks about something called splitting and filtering. The ATLAS experiment was using that.
Splitting and filtering. So they were literally like filtering out the noise.
Essentially, like sifting through a giant pile of evidence looking for the key clues.
So you're looking at this jet, this spray of particles, and you're trying to isolate.
The most important parts. The ones that are most likely to tell you about the original particles that decayed.
And did it work?
Surprisingly well, actually.
That's impressive. But it wasn't just about cleaning up the data, right? They were also interested in the shapes of these jets.
Ah, yes, the shapes.
Yeah.
Because just like different fireworks make different patterns, different particles leave behind unique energy signatures.
So by studying the shape of a jet, you can start to deduce what kind of particle created it.
You got it. Like a fingerprint at a crime scene.
That's pretty cool. But I'm guessing it wasn't always easy to interpret those fingerprints.
Oh, definitely not. It gets really complicated really fast.
How so?
Well, one of the things they realized early on was that to really get those shapes right, you had to understand some of the messier parts of particle physics.
Messier. How?
Well, for one thing, there's something called the underlying event. Basically, all the other stuff happening in a proton collision besides the specific interaction you care about.
So it's like background noise.
Exactly. And then on top of that, you've got these quarks, you know, the particles that make up protons and neutrons.
Right.
Well, quarks don't like to be alone.
They're social butterflies.
Well, right. So after they're produced in a collision, they immediately start combining with other quarks and gluons to form new particles.
Which makes things harder to track.
Oh, yeah. Trying to trace back those individual quarks after they've already formed new particles, that's a real challenge. And then
There's more.
they were also really interested in finding a very specific particle.
Let me guess. The Higgs boson.
Not quite. This was before the Higgs discovery. They were looking for something else, something even more elusive.
Ooh. Now I'm really curious. Don't leave me hanging. What were they after?
The top quark.
The top quark. Why was that so hard to find? I thought we already knew about that back then.
We did, but these guys were looking for top quarks that were really, really moving, like close to the speed of light.
Boosted, you mean?
Exactly, boosted top quarks. And when something's moving that fast, it gets really smushed up. The decay products, they get squished together. So instead of seeing a nice clear signal, you get this really messy jet.
That makes sense, I guess. But how do you even begin to find something like that?
Well, that's where things get really interesting. They had to come up with some pretty clever tools.
Like what?
Well, one of them was called N-subjettiness.
N-sub-wetness.
N-subjettiness. It's a mouthful, I know.
So what does it do?
It basically tells you how likely it is that a jet came from a specific kind of decay. Like, if you think a jet might have come from a top quark, you can use N-subjettiness to see how well it matches up with what you'd expect.
Like a probability score?
Kind of. Lower score means it's a better match.
Got it. Anything else in their toolbox?
Oh, yeah. They had a whole bunch of tricks. They were also looking at something called depolarity.
Depolarity. Okay, now you're just making up words.
I know. But it's actually pretty cool. Remember how we talked about color charge?
Vaguely. Remind me.
Right. So it's like electric charge, but for the strong force. It's what makes quarks stick together.
Right.
Well, it turns out that the way color charge is distributed in a jet can tell you a lot about what kind of particle it came from.
So like different particles have different color signatures.
Exactly. And dipolarity was one way to measure those signatures.
I think I'm starting to get it. What else?
They even tried using templates.
Templates, like for arts and crafts.
Not quite. They were using computer models to create these templates of what they thought different kinds of jets should look like.
Oh, I see. So they'd compare a real jet to these templates and see which one it matched best.
Exactly.
That's clever. But how did they know if any of these tools actually worked?
Well, they couldn't just assume they did right. They had to test them.
So they did some experiments.
They used simulations. They basically created these virtual universes where they knew exactly what was going on.
Oh, so they could control all the variables.
Exactly. And then they let their algorithms loose on these simulated events and saw how well they could identify the boosted top quark.
What did they do?
Well, it was a mixed bag. Some methods worked better than others.
Any clear winners?
The ones that did some kind of grooming beforehand tended to do better.
Grooming. Now they're really getting fancy.
Basically, it's a way to clean up the jets before you analyze them. Get rid of any stray particles that might be messing things up.
Ah, so like tidying up the data.
Exactly. And one of the methods that used grooming and seemed to work really well was, you guessed it, n-subjettiness.
So it all comes back to n-subjettiness. That's pretty impressive. But this was all happening back in 2011, right? What were they still hoping to figure out? What were the big unanswered questions back then? So what were the big mysteries they were still wrestling with back then?
Well, one thing they kept coming back to was the challenge of measuring jet mass.
Jet mass. Seems pretty basic. What's so hard about that?
You'd think it would be straightforward, right? But it turns out that when you're dealing with jets that have really small masses, things get tricky.
How so?
The equations we use, they start to break down at those tiny scales. The approximations we usually rely on, they don't work so well anymore.
So too small to even measure.
Kind of. It's like trying to weigh a feather on a bathroom scale. The scale just isn't sensitive enough.
Makes sense.
Yeah.
So what were they hoping to learn from those low-mass jets?
They thought those jets might hold clues to some of the biggest mysteries in physics. Things like dark matter, dark energy.
Really big questions.
Exactly. They were wondering if maybe, just maybe, those tiny discrepancies in the jet mass calculations could be a sign of something new.
Something beyond what we currently understand.
Exactly. Like, what if there are particles out there that are so light they've been hiding from us this whole time?
Hiding in plain sight.
Right. But it wasn't just about the mass. They were also trying to get a better handle on color flow.
Color flow. We're back to the rainbow jets.
Yep. They knew it was important, but actually modeling it, that's a whole other can of worms.
Worms. That's an interesting analogy.
Huh. But you get the idea. It's complicated stuff. And then, of course, there was the whole issue of hadronization.
Right. The quark after party. That's still a problem.
Oh, yeah. Trying to figure out exactly how those quarks and gluons combine to form new particles, that's a tough nut to crack.
So many puzzles.
That's particle physics for you. Always more to discover.
Well, this has been fascinating. I had no idea how much work went into understanding these jets.
It's amazing what they were able to accomplish back then with the technology they had, and it really laid the groundwork for what we're doing today.
So where do we go from here? What's next for jet substructure?
The search continues. We're still looking for those new particles, those hints of physics beyond the standard model. And we're developing even more sophisticated tools to help us do it.
It's like having a more powerful microscope.
Exactly. We're constantly pushing the boundaries of what we can see and measure, and who knows what we'll find next. That's what makes it so exciting.
That's the beauty of science. It's a never-ending journey of discovery.
Couldn't have said it better myself.
Well, on that note, I think we've reached the end of our deep dive into jet substructure.
It's been a wild ride.
From pile-up to boosted top quarks, it's amazing to see how far we've come, and who knows what incredible discoveries await us in the future. So until next time, keep exploring, keep asking questions, and never stop searching for those hidden truths about our universe.
You hear?